Okay. Hello, everyone. Welcome to the last TAP colloquium of the semester. I see that attendance has also stabilized online, so welcome to people attending remotely as well. Today, we're lucky to have Kimberly Boddy from the University of Texas at Austin visiting us. Kim did her undergrad at MIT, then got her PhD at Caltech, and after a postdoc at the University of Hawaii and JHU. She has been junior faculty in physics at Austin since 2020. She has been working on a broad range in theoretical astrophysics, cosmology, and particle physics. And today she's going to tell us about her search for dark matter interactions through our cosmic history.
Thank you very much for the invitation. Do I need to be by that computer to be heard? Oh, I have the microphone. Okay. Thank you. So I'm very happy to be here. I'm very happy to be here in person. It's been a long time since I've traveled to give a talk. And so I'm going to be discussing possible different interactions that dark matter could have that are going to go beyond our standard lambda-cesium cosmology, in which is assumed to be some non-interacting matter component of the universe. And please, at any time, if you have questions, I welcome interruptions, and we can get those questions settled as they come. So to begin with, let me just give you an outline of what the talk is going to look like. So at the beginning, I'll just sort of give an overview of what the role of standard dark matter is, just so that we're all on the same page. And this will also be an opportunity to kind of set the scene for what we're going to do in terms of making dark matter have some sort of non-trivial physics. In particular, I'm going to be looking at scattering processes that dark matter can have, and this is going to be scattering with standard model particles. And so the overall effect of dark matter scattering that I will discuss is a suppression of small scales. And then I'll also talk about briefly the impact on 21 centimeter observables and with some future prospects. So let's jump right into it. The role of standard dark matter. So to do this, let me go ahead and focus on this schematic that we have for the timeline of our universe and discuss what's going on. So we have the Big Bang over on the left, and time flows from left to right. And the early universe, very early universe, everything was dense, hot. All of our particles were completely ionized. And Big Bang nucleosynthesis occurs about a handful of seconds to a handful of minutes after the Big Bang. And this gives us our light element abundances. And so there's a lot of hydrogen nuclei running around, and a little bit of helium, and then much less of the other heavier elements. So I'm just going to assume for the purposes of this talk, we just have hydrogen and helium in our universe. And it is not until the cosmic microwave background that when neutral hydrogen forms, that the photons in the universe are allowed to more or less free stream. And we can observe this radiation today that was essentially emitted at about 380,000 years after the Big Bang. Okay, so after the cosmic microwave background was formed, we enter this period called the Dark Ages, in which the universe was mostly neutral. And this Dark Ages period is one in which there's just not a lot of observational signatures that we can directly probe what is happening during this period of time. And it really isn't until this epoch of cosmic dawn, when the first stars form, that something new happens that we can hope to observe. Okay, and then of course, as the universe continues evolving, we have the universe becomes reionized, and we have today's galaxies that we can observe about 13.8 billion years after the beginning of the universe. So this is the rough overall picture. And so dark matter plays a very important role in this whole story because dark matter is responsible for all this formation of structure that occurs from early times to late. So the observations, the observables that I'll be interested in are these ones at the top, the CMB cosmic dawn in today's galaxies. So that will be the focus. And so to start out, let's begin at the beginning and talk about the cosmic microwave background. So the CMB has a lot of structure to it. We have very good data that we've observed from this. And so we need to understand where all these temperature fluctuations in the CMB come from. So these come from acoustic oscillations, and the very rough picture that you can imagine is that you have a potential well, gravitational potential well, that an overdensity of dark matter has created in, say, a location given by this potential well here and maybe this one here. And so my baryons that are in purple feel the gravitational pull from this dark matter overdensity. And so you have this rough picture that baryons are going to infall. In these early epochs, though, before the CMB actually forms, these baryons are tightly coupled to the radiation in the universe. And so there's something that looks like radiation pressure that is pushing this baryon and photon fluid back out of these potential wells. And so you can imagine this happening on a variety of scales, right? And so we have this oscillatory behavior that happens at different frequencies, different wavelengths, and this is essentially the Fourier space description of what's happening in the early universe. You just have a bunch of harmonic oscillators, and there's going to be friction terms, there's going to be coupling terms, but this is the rough idea of what you should have in mind. Okay, so for the measurement of the CMB, when you have neutral hydrogen forming, you release the CMB radiation because the radiation really wants to interact with all the electrons, free electrons in the universe, and when there are no more free electrons, that's how you get this picture of the CMB. And so early days of COBE, we actually got a measurement of what the temperature is of the CMB black body. And so it's very close to 2.7 Kelvin. But we can also measure all of these fine structures that exist in the CMB. So these are all temperature fluctuations of the CMB photons that are around this 2.7 Kelvin mean value. And so these fluctuations are on the order of like 10 to the -5. And so these are very, very small fluctuations, but they give us a lot of information about what was happening at that time that the CMB formed. And so here's the data from the Planck satellite. This is the temperature power spectrum. This is the polarization power spectrum. And this underlying gray curve for each of these data sets is the standard lambda CDM model, okay? And so a lambda CDM fit to these data incorporates this component of dark matter, in which dark matter is a cold and collisionless fluid. It has to be distinct from the baryons because it can't be coupled like the baryons are coupled to the radiation. Dark matter needs to be the potential wells, gravitational potential wells that are sitting there in the early universe for the baryons and photons to slosh back and forth in. And so dark matter has to be, it turns out, about 6 times more abundant than baryons to give this nice fit to the CMB. And so when I say baryons, what I mean is we have our protons, our ionized hydrogen in the early universe, we have our helium nuclei, and we have these electrons that are there as well, okay? So this is, fantastic data that we have from the CMB. And so what do we do with this? We have this picture that dark matter is there. It has to behave as matter. And so where exactly does it fit in terms of being a particle? We have particle descriptions of all the other matter in the universe. Why not this one? And so this sort of spawned the weakly interacting massive particle picture, where you have two dark matter particles that can, say, interact with two standard model particles in some way. And in the early universe, you have this equilibrium that occurs at high temperatures, where you have production of dark matter from two standard model particles and the annihilation of dark matter into standard model. And so the typical story of these weakly interacting massive particles in terms of WIMPs is that you have some co-moving number density that you can compute. And as dark matter is becoming more and more non-relativistic, and these interactions are becoming biased in terms of dark matter can annihilate, but then there's not enough energy for the standard model particles to create dark matter, you start getting this Boltzmann suppression of the number density. And so eventually, though, Hubble expansion does win, and it will freeze out this annihilation process so that the dark matter stops this exponential decay. And that tells us what our relic abundance is. So if you make a simple assumption about what this annihilation cross-section should scale as in terms of its coupling and in terms of the mass of the particle, you get what is called the WIMP miracle. And so this is the coincidence that if you have literally weak scale particles, if you have a weak interaction with a weak scale mass, as in the weak force, you can obtain the correct relic abundance for dark matter. And so this has spawned a lot of work into thinking, oh, okay, if we have supersymmetry, we can have the minimal supersymmetric standard model. The lightest supersymmetric particle could be this WIMP. Okay. Yes.
Sorry, alpha, is that defined structure constant or just some coupling constant?
The question was, is this alpha some defined structure constant or just some coupling constant? This is actually, if you want to think of it in terms of the WIMP miracle, this is alpha weak.
Okay.
Yeah. And so this this idea, this WIMP scenario is actually really nice. It fits really nicely. And so there have been a lot of efforts, dedicated efforts to go and search for this type of interaction. So in terms of production, we have, these linear colliders at CERN that are trying to produce some new evidence of supersymmetry, for instance. But no supersymmetry has been observed. For annihilation, we can think about where is this dark matter located, right? It's located in dark matter halos that are surrounding galaxies. So maybe we can observe some dark matter interaction indirectly by looking at the products that it creates when it annihilates. And so there have been hints that maybe some process is going on like that, but nothing that the community generally has uniform agreement on. And so there's also the process in which you can read this diagram from left to right and look at a standard model particle and a dark matter particle just simply scatter with each other. Okay. And so that is the interaction that I want to focus on. And a lot of work has been done in terms of what's called direct detection. And so here's a stylistic picture of what the Milky Way looks like. We are moving in the Milky Way. And so in our frame, there looks to be this wind of dark matter WIMP particles that are flowing towards us as we move around in the galaxy. So the idea is to build big detectors with liquid xenon, liquid argon, and the idea is to hope to see this recoil event of a dark matter particle coming in and scattering with one of the atoms in the detector. And so this is the idea behind nuclear recoil. It depends on the rate at which this happens, depends on a variety of things. It depends on astrophysics, particle physics, and experimental sensitivity. So the direct detection program has done a lot of work in terms of probing very, very sensitive cross sections. And so here's a plot of the dark matter mass on the x-axis against the dark matter nucleon cross section for a very particular type of interaction. And so this is a contact interaction. There's just a constant cross section. And 1 GeV, to give you an anchor, is about the proton mass. So all of these experiments that have occurred have just been placing these exclusion limits. There's no evidence for direct detection of dark matter that is accepted. And so there are a couple things to note: that this plot does not go up arbitrarily high. These exclusion limits have to cut off at some point. And it's because if you have a large enough cross section, all of these experiments here are placed deep underground. And so if you have dark matter that has a significant interaction with standard model particles, then they're going to scatter in the atmosphere. They're going to scatter in the crust of the Earth. And that completely changes the story for being able to detect them in underground detectors. So there's going to be some ceiling of sensitivity that they're going to be sensitive, that these experiments are sensitive to. The other thing to note is that as you go to lower dark matter mass, the ability for these experiments to read out whatever nuclear recoil events occur from possible dark matter is just not going to be large enough for lower masses. So there's two limitations that direct detection does have, even though they have done extraordinarily well in constraining the standard WIMP parameter space. A similar story can be said for interactions with electrons. And so people have been thinking, let's go and look at electronic recoil. And that way we can get to lower dark matter masses, but you're probing a different type of interaction. So this is the story of direct detection. And I wanted just to provide some context for this whole setup in terms of what the particle physics community has been doing and their efforts in trying to understand what interactions dark matter may have. And so the idea is that we can search for this exact same physics, but we can do it with cosmology. And we're going to be able to probe regions that are very complementary in terms of parameter space, and search for this exact same type of physics that is done with these large underground detectors. So what happens when you introduce this dark matter scattering into the picture? So the relevant eras that I'll be focusing on for this section of the talk are the CMB and halo abundance measurements. And so starting with the CMB, we had this picture where we had this potential well. And now if we have actual dark matter particles that are making this gravitational potential well, and there is a baryon that's falling into it, and it interacts, it can kick one of these dark matter particles out of its own potential well because there's some interaction. So that's the particle description of what's happening. The cosmological fluid description is that when you turn on this collision between these two fluids, it creates a drag force between them, okay? And so what happens overall is that interactions get just washed out for small scales. If you have a very, very small potential well, it's very easy to break those particles up. And this is something that can be tested with or looked for in the CMB. So in terms of what we have to do, what kind of models we can consider, we have to think about the particle physics at hand. So the momentum transfer cross-section is what cosmology cares about. This is when you put everything into the Boltzmann equations, you follow all the calculations through. What the Boltzmann equations want is this weighted cross-section. Okay, so we're going to parameterize this as some magnitude, some constant prefactor. And so this is the thing that we're going to fit for. using data. And it will have some dependence on the relative velocity between these two incoming particles, between our dark matter that I'm calling chi and our standard model particle, whatever it may be, that I'll just call F. And it has some power law dependence here. So this is just not an arbitrary parameterization. I don't want to go through all of this, but there are definitive models that I can write down that you can, there are definitive models that you can write down for dark matter that give you this very generic dependence on the velocity. So for heavy mediators, what I mean by that is essentially anything that has a non-negative velocity dependence. If you want to get a v to the -2 or a v to the -4, you have to start thinking about different, slightly different models. So this would occur if n equals 2 would occur if dark matter has an electric dipole moment, for instance. Or n equals -4 would occur if you had dark matter that actually had some electric charge to it. It's certainly not going to have E electric charge, but it may have some fraction of E as its charge. So here in the early universe, the relevant particles that you could consider are, your electrons, your protons, and your helium nuclei. Okay, so I'll show you one more slide of equations and I'll be done. And so this is the, well, I'll be done with the equations. So here's how the Boltzmann equations get modified. If you're used to thinking about Boltzmann equations, great. That's how these are the new terms in red that come about. If you're not, don't worry about it. The thing to focus on is that there's this momentum transfer rate. So how much momentum is being transferred to and from the dark matter fluid interacting with baryons. And so you have, this A, which is just the scale factor. You have the number density of your target particles. And there's this sigma naught that is our parameter that is telling us what our particle physics is. And then you have various factors of mass and temperature that come about. You also have a very similar looking formula for the amount of heat that's transferred between these two fluids. And there's, I'll just mention that there's a very technical issue. If somebody is interested, I can discuss it later. But there's an issue that if you have non-trivial bulk velocities that come into play, then your equations have to be modified. So this can all be coded into class and run to actually do a cosmological fit for this interaction that occurs. So the momentum transfer rate is really the thing that's appearing in these equations, right? And so this is what cosmology cares about. So I want to show you what this momentum transfer rate looks like. So here's the momentum transfer rate on the y-axis divided by the Hubble expansion rate of the universe as a function of redshift. So if you are at this gray line right here at 1, this means that above this line, you have some amount of efficient scattering that's happening over Hubble. If you are below this line, it means that Hubble expansion is winning and preventing interactions from being very efficient. So we can think about all of our different models that come from various velocity dependencies. And so you can see for, say, this red line at the bottom in the legend, a v to the 4 interaction is going to have a lot of interaction at very early times and much less at later times, okay? And it's not until you get all the way down to v to the -4 that you actually change the slope of these lines, where you have a little bit of moderate scattering at early times, and the importance of this scattering term grows later. So these are all going to give you different effects in how your CMB power spectra get altered. All right, so that was the momentum transfer rate. We can now essentially take everything that I showed you and do a cosmological fit, vary all the standard cosmological parameters. We have a new parameter, sigma naught. Just to not have the number of parameters grow too much, we can think about the different masses, each individual particular mass. But first, let me show you how actually the power spectrum changes. Here's our power spectrum for our CMB, and this is the lambda CDM best fit. If I turn on a lot of interactions, this is what happens. So you have this, well, you have a couple different effects. The first minor ones are that you have this very, very slight enhancement of your first peak. You have that the peaks get shifted a little bit, but the thing that actually drives any constraint on this is this suppression that happens at high multipoles. And so this is the silk damping that occurs in the CMB. It's like the silk damping that occurs in the CMB. It's just that your CMB gets damped more because of these interactions. So this is, well, clearly this model is well ruled out. You can see by eye the differences between these two power spectra. And so the higher that you make this cross section, you'll get more and more suppression up to a certain point. So we can see if the CMB has any preference for having such an additional damping or not. It turns out not. But with that information, we can set constraints. Yes.
Sorry, I'm not up on, you know, how you read the wiggles in the CMB.
Oh, yes.
But I know you're reading that, or not you're reading that, but one reads that to get, you know, several parameters. There's a lot of covariance between them. And as you're presenting this here, you know, small scale suppression, you know, is orthogonal or completely independent of that. And I'm wondering if in fact there are covariances. In other words, if you saw that, you would have different things for baryon density and other things, which might not lead you to, you know, believe that small scales are being suppressed, but there is another optimal combination of cosmological parameters, if you see what I'm asking.
Yes, yes, exactly. So that's a great question. So the comment was essentially, if I can summarize, about the degeneracy of other cosmological parameters. Yeah, exactly. So amazingly, there is very, very little. There's basically no degeneracy with any of the cosmological parameters except the tilt of the power spectrum.
Okay.
Because the tilt of the power spectrum is literally
Is what
controlling.
you're seeing, yes.
Yes, exactly. It's literally controlling how much. I mean, tilt is a very good word. It's controlling the tilt of the power spectrum. And so there is degeneracy with that, more so for certain models than others, but yeah, it does change that. Yeah. Did that answer your question?
Yeah, it did. Thank you.
Okay, great. Okay, so now that so this is what happens. Now we can actually take Planck data and actually make a fit. So we do, you know, our temperature polarization and our lensing. Anisotropies, and these are the scattering constraints that we get. We have dark matter mass on the x-axis in both of these plots. These are for different velocity dependencies. The left versus the right plot is whether you are scattering with protons only. And so this is not including the protons within helium. This is just hydrogen, essentially, and scattering with electrons over on the right. Okay, and so out of context, these, you know, these cross sections, okay, they're there. We've placed limits on these different models. Give me a few minutes and I'll actually put some of this into a little bit more context into other constraints that are on these different models. But I first want to introduce something else. So keep this in mind. We've placed constraints with the CMB. So, right. Okay, so I'll do a little bit of that now, I guess. The n equals 0, so this is no velocity dependence. This is only interactions that are constant. And so you can see there are limits from spectral distortions. These are older works. This is, you know, from 2018 when we only had Planck 2015 data. but we have two different lines here that I want to draw your eye to. So this is scattering with only the hydrogen in the universe. Oh, sorry, this thinner red line is scattering only with hydrogen in the universe. And this darker red line that's lower is when you add the ability to also scatter with helium. If you scatter with protons, you necessarily typically have to scatter with helium unless there's something telling you you can't. But the incorporation of helium scattering is a bit model dependent, but it's important if you have large masses for your cases of being greater than or equal to 0. And so the reason that this is important is that it wasn't really appreciated for how important helium scattering is. Over here in the high mass region, this line here, even though helium has a mass fraction of, about 0.24, there's not a lot of helium in the universe compared to hydrogen, but the scattering with it is so important for these types of models at high masses that that's the only thing that matters. And so not including helium is doing a pretty big disservice, and is possible that dark matter could even not scatter with protons at all. It could have some preferential scattering with neutrons. You can have some model that realizes that, and then you're not scattering with any hydrogen. You're just scattering with helium. And so this was work that was explored by my graduate student, Stacy Moltner, in a recent paper. So that's.
Ruby, could you say what the difference between neutrons and protons are in this regard? What, I mean, why would they be different to a dark matter?
Oh yeah, so so before everything is, let me start that again. So you have hydrogen nuclei protons, right? And the helium nuclei have, are going to have 2 protons, 2 neutrons. So there are not going to be any free neutrons around because, yeah. And so if you have some sort of maybe isospin violating dark matter interaction, you can have situations where dark matter only communicates with neutrons and not at all with protons. And so then then dark matter is only going to see the neutrons and helium and not going to care a bit about all the hydrogen that's running around. So good. There we go. That's the scattering in the CMB story. The next thing I want to point out is that if you have all these small overdensities in the early universe that get washed out, then they don't exist later to start to continue to grow and eventually collapse and have nonlinear evolution to actually form structure. So here's a simulation, an old simulation that just has a very generic comparison between a dark matter only simulation that has some large galaxy here that's, or some dark matter halo here that's hosting a lot of substructure. And if you just have a generic small scale suppression like what we've been talking about, you see that a lot of this structure gets washed out in this right plot over here. So we have a lot of substructure, and the substructure that we're able to see the best, that is the faintest, are the ones that are nearby. So here's the Milky Way halo, and here are a whole bunch of identified Milky Way satellite galaxies. And so there's our classic dwarfs that we've known about for a while in orange here, and then in blue are those that have been identified, or some of them that have been identified by the Sloan Digital Sky Survey. DES and Pan-STARRS have also seen dwarf galaxies, and so you can use this information to say, well, you can't have interacted or had this interaction. Dark matter can't have washed out too much structure such that you don't even get these galaxies, that you wouldn't predict that the galaxies of this size would exist in our own Milky Way. And so you can look at, this is the linear matter power spectrum that you have if you have dark matter interactions versus what it looks like just in lambda CDM. And you see that there is this cutoff of the matter power spectrum as you get to small scales. Okay, so lambda CDM would just be 1 across the board. And depending on how big your interaction is, changes where this cutoff happens. So it turns out that this looks very, very similar. These transfer functions look very similar to that of warm dark matter. And so this is, so these are the effects that you would observe. And so let me skip the velocity dependent models or talking in detail since I'm running a little short on time, but but you can derive limits based on the constraint that we have from just the observation of these dwarf galaxies and the population of dwarf galaxies we have in our own Milky Way to set constraints on the cross-section that is allowed between dark matter and ordinary matter. Okay, so those are constraints. Let me give you some larger context here. So if we imagine scattering with protons, we're going to pick our favorite n=0 case. This is the dark matter proton cross-section against dark matter mass. And this is the CMB bound up here. These are, this is the Milky Way satellites bound, that's orders of magnitude stronger. And over here, if you remember all the direct detection limits that I was showing you, these direct detection limits go all the way down to, 10 to the minus 44. So we're at, this is a marker of 10 to the minus 30. And so these direct detection experiments are probing things way down below this plot. But there is an estimated ceiling that theorists have come up with in terms of what actual sensitivity reach these things. And so you see that these cosmological probes, they don't have any threshold issues about, we have to have enough nuclear recoil energy to be able to detect it in an actual experiment. It doesn't really matter what mass your dark matter is, as long as it's not, too light to start behaving differently than matter, than normal non-relativistic matter. But if you have, very, very light species, it doesn't matter at all to the CMB. CMB is going to be able to see it, or the early universe is going to be able to see it, and that has consequences for both the CMB and the formation of structure. Okay. So that's what cosmology is able to do for you. It probes very high cross sections and goes down to low masses. In terms of scattering with electrons, the situation is a little bit different of the certain types of models that people think about. So this is the equivalent picture of the one I showed on the previous slide. But this is, for instance, for n=-4, here where all the direct detection limits lie, once again, at high relatively low cross sections and high dark matter masses. And the CMB constraint actually starts doing really well at lower masses and is intersecting these direct detection bounds as they are typically plotted in result papers. So that kind of gives you the context for what we're dealing with here and what cosmology is able to do for you. Yeah, so that's the story with the small scale suppression story. Okay. And so now I want to turn to this other effect that is relevant for cosmic dawn. And the idea, so this is a very, very schematic overview. I don't want to go into the details of what the 21 centimeter detection looks like, but we're talking about looking for a global signal of 21 centimeters. So what do I mean by that? I have So this is post-recombination, this is post-CMB formation. And we haven't had the formation of the first stars yet. And so we just have these clouds of neutral hydrogen that exist, and there are CMB photons that are streaming by. And so between us with a tabletop experiment over here are seeing these CMB photons, but they have to pass through these clouds of hydrogen. Now, neutral hydrogen in its ground state has two hyperfine states. It has a singlet and it has a triplet, and this is due to the spin interactions. And so, you know, you have a large population of ground state hydrogen. The hyperfine splitting is excited in some cases, but at the right temperature of the CMB photons, this hydrogen can absorb one of those photons and be excited. And so this 21 centimeter hyperfine transition can just take one of these photons away. And that's very basically the effect that you're looking for. So the CMB serves as a backlight. It shines on these hydrogen clouds, and you're looking essentially for a deficit in absorption of CMB photons. It's a little bit more complicated than that in the sense that, you know, there are already a population of excited states. So you have both emission and absorption happening. And so something has to tip the balance in order to actually see CMB photons being lost without you regaining them from an other excited hydrogen state relaxing and giving you that photon back. So it happens that one of those signatures that, that you can hope to see this difference, this absorption, is right around the time of cosmic dawn, when and it's because the first stars turn on and they start emitting radiation that can excite hydrogen into the Lyman alpha series. And when it decays back, it populates, it sort of jumbles around and randomizes the population of hydrogen in its hyperfine and its in its triplet and singlet state. So that is the trigger. That is the era that we're talking about. And the EDGES experiment actually has claimed to see some absorption signal. It's a very strange looking signal compared to what was expected theoretically. It's also much deeper than what was expected in just sort of standard cosmology in some extreme scenario. So it's also at a frequency that is pretty high in redshift. So this would be indicating that you know, the first stars turn on and the initiation of reionization began at like Z of 17, which is quite high. And so there was an argument that said, okay, well, let's just imagine that this is a real signal and we can get a very large absorption trough if we have some situation in which you can cool the baryon gas. And by doing this, very roughly speaking, you can think about it, you cool the gas enough and it allows the absorption of more CMB photons. So a V⁻⁴ scattering, the claim was, can do this for you. And this situation was studied in years prior to this EDGES announcement. But we can go and we can say, you know, I've been talking about this scattering story, and you can ask, is it consistent with the CMB? And here's the CMB constraints in these contours. This is a very rough projection for what CMBS4 could possibly do. And here's the cross section that you would want if you wanted to explain this EDGES signal. So it's well below that of the CMB. Great. That is far from the end of the story. So there's a lot of issues with how these lines get drawn. One of them is that it's assumed that dark matter that's interacting doesn't affect the matter power spectrum, but it very much does. Even a little bit of scattering in the early universe can suppress the matter power spectrum. And so that's not incorporated into this. And that changes the story quite a bit in terms of being able to have this, this picture give you anything that looks like an edges signal. You also have this issue of, are you talking about scattering with neutral hydrogen, or are you talking about scattering with an ion? And this is very important for particle physics, because scattering with neutral hydrogen is a difficult situation to think about how that could possibly come about. There's a lot of constraints that come along with this. It usually enters in the sense of you have fifth force constraints, because there has to be some mediating particle that controls this. So this is a highly constrained scenario. And this other scenario, dark matter ion scattering, can happen. I mentioned a while back ago that dark matter that has a very, very small amount of electric charge can give you a Coulomb interaction. And so that's good. That's a model. The CMB constraints that I showed you are perfectly fine with either, because all this scattering is happening when everything is ionized anyway. When you think about later universe, during cosmic dawn, you have everything that's very largely neutral. So the ionization fraction is really low. The amount of ionized particles is just low. So you need to actually take these lines and push them up quite a bit, so that there is completely disallowed by the CMB. So the solution, the workaround to that, is to only allow a very, very small fraction of the dark matter behave in this manner. And so you can do that. So, we tested this, and if you just allowed the fraction of dark matter to vary, you can see that Planck eventually loses sensitivity. And this is because you're contributing such a small portion of this millicharged dark matter, this interacting dark matter, that it starts hiding itself as just a very small component of baryons. And so you're essentially losing sensitivity because you're hiding this component of dark matter in the baryon density uncertainty. So, below about 0.4% of dark matter, of all dark matter, with the rest behaving as just normal lambda CDM, Planck can't constrain this. And so, the viable parameter space for this story to explain edges is fairly small. And in this paper, we are being very generous to it. This parameter space is essentially not viable either. So it's a very, very narrow region. But I don't want to have you leave this story thinking that this effect that can impact 21 centimeter physics is all about edges. It's very much not. If you have this type of model, if you have this sort of dark matter, this effect is going to be there. And we have plenty of other experiments that are coming online to comment on both the edges measurement and on possible new physics to probe from the era of cosmic dawn. Okay, so with that said, let me just end on sort of some future prospects that we have in each of the three different observations that I've discussed. And so in terms of CMB experiments, we've come a long way from COBE to WMAP to Planck. We have ground-based telescopes that can be built much larger. And so they have are able to resolve finer angles in the CMB sky. So we have the South Pole Telescope and the Atacama Cosmology Telescope. And upcoming are the Simons Observatory and CMBS-4. People are already thinking about future probes as well, but these ones are expected soon or within the decade. In terms of galaxy surveys, I've just picked a line of succession of a specific type of survey from SDSS to DES to the Rubin Observatory. There are certainly a bunch more, and the hope is that maybe we can see that if you go to small enough dark matter halos, that maybe there's some sort of cutoff that we can actually observe. And that would give us information that something is destroying small scale structure, and what that something is something to be discussed and looked into. And then for 21 centimeter experiments, we have a variety of instruments that can follow up on the edges signal for the global signal, but you can also imagine observing the fluctuations across the sky of the 21 centimeter signal and looking at the power spectrum. And so this is, being done by Hera, and future SKA will comment on this. So very last slide, I just want to leave you with this slide of essentially complementary probes of astrophysical and cosmological probes that can access dark matter across a range of times. And so this is essentially at different energy scales and a range of different length scales or halo masses. And so if you have this sort of landscape of different experiments, of different cosmological experiments that are both coming up and that are probing all these different mass and energy regions, they're going to be sensitive to different types of dark matter models, and understanding the interplay between all of these things is going to be a very exciting time in the upcoming decade as experiments turn on and data starts flowing in. So I appreciate your attention, and I'm happy to take any questions. Thank you.
Back to slide 15, you showed CMB spectra, and you said a very strong interaction there. Was that velocity independent?
It was.
Okay, and sigma naught then was the only thing you were varying?
Yes. Velocity independent interaction. The sigma naught, I think I had to boost like at least 6 orders of magnitude above its.
But a good example. I kind of expected you to then take the dotted line is CDM, take a CMB spectra and then vary N.
Very
What
good.
if you did that?
Yes, that's a good question. So the varying the tilt, that's a good idea. I will include that in future slides. So varying the tilt will try to recover some of that, but you're tilting the entire spectrum. And for this particular model, there's a little bit of degeneracy, or there's a little bit of correlation, but not a lot. For other models, which I haven't shown you the power spectrum for, the degeneracy is much more significant. So I could do that trick of just changing the tilt, and it would look very similar to the other spectra. The thing that helps differentiate that is that we also have information about the lensing anisotropy that's from the CMB, and so that information is not affected by the tilts. It's very much affected by how much matter there is.
And so in the CMB data at the small scale today, you can't see that. You think in the future with larger apertures, smaller scale structure, we'll be able to actually vary those ends and see which one of those it is?
Yeah, so certainly as you go to higher and higher multipoles, this becomes the ability to constrain this is just going to get much better, right? And so it's just that for this particular one, if I just tried changing the tilt, it wouldn't look very much like this. That's what I'm trying to say. There are other models that I could have plotted for you that it would.
Right.
But not this particular one.
Thanks.
Yeah.
Is there enough cross-section in dark matter to become virialized?
Is there enough cross-section in dark matter to become virialized? So a lot of these models that I was talking about, there is a dark matter temperature, and it matches that of the CMB at early times. You start the motion of the photon baryon fluid, the dark matter starts to match the motion. It's not quite like a tight coupling regime. But yeah, I mean, your dark matter temperature is completely thermalized with the photon bath. Is that?
Okay, and wasn't there an announcement last week that someone had repeated the edge observations and didn't find any?
Yeah. So was this last week? So there are a couple of experiments that are going on. One of them, I believe this is Sarah's, didn't find anything consistent with edges. So this is why I ended the discussion on 21 centimeter, and that this whole story is kind of got started or picked up a lot of attention from edges, but you know, it's phenomenology that we can expect even if the edges signal goes away. It's still a prediction that we can make and look for when we actually see a 21 centimeter signal that we can be confident about.
Are there more questions also online? May I ask one more about, I guess, especially the Milky Way satellite constraints future surveys?
Yes.
What astrophysics would you like astronomers to really solve for you the most to interpret future satellite counts?
That's a fantastic question. So what sort of in rewording, so sort of what I would consider a systematic to figure out in terms of galaxy number counts. So I mean, there has to be some amount of simulation work that really needs to be done. It kind of only matters if we actually see something. But you know, you don't know if you're going to see something, and so you want to kind of be prepared for that with the next data set. The difficulty is how, you know, what are the uncertainties in the sense of if I plot a subhalo mass function, what am I really, how confidently can I tell what that shape is? Because if I can, you know, be specific, if I can say, here is the measurement and here is my simulation, and these have like infinite precision, let's just say, well, then it can be easy to say, this type of model produced this spectrum. But if you don't have that at the moment, it's just a constraining tool. It's not a discovery tool. And I think that we need to understand, especially the in-between simulation talk. We really need to understand what features of the halo mass function or what have you go into sort of confounding what we can say about the dark matter parameters. So I think a large portion of it needs to be on the simulation side.
I'll look around once more. Any other questions? If not, thank you very much for this fantastic overview.